So for gravity, gravity is actually not really the correct term when we talk about we have gravity on something. Gravity is a result of a large object. Any large object, we talk about a celestial object, being a planet or a large moon or something like that, or a star. Anything that is large will have its own gravity, meaning that it pulls objects towards its center. So that's why we don't just say pull towards its surface, because if we were on Earth, well, we are on Earth actually, and we were to dig a hole, a really, really deep hole, will we stop moving at where the surface was, or do we still have attraction towards the ground? We still have attraction towards the ground because gravity pulls towards the center of the object. So if you were to dig a hole, as you know, really, really deep hole, right? Gravity will continue to pull you down. Now, there's no way we can dig a hole from one side of the planet and go to the next side of the planet. That does not exist. That cannot happen because, you know, below our planet, below the surface, below the crust, it's really, really hot. So you're going to melt before you even reach the next side. It's not going to be pretty. Okay, so this constant pull, right? As if I had an object. Now, this is why I did the lab before we did this topic. If I have the ground and I were to release that object, meaning I hold it and I dropped it, it's going to fall towards the ground. It's not going to stay there. We're talking about, you know, a sizable object, right? A little dense object. It's going to fall towards the earth. And it does so with the same acceleration, or generally the same acceleration towards the earth. Now we call this acceleration the acceleration due to gravity, because gravity is the attractive force exerted by a large object on another. And the average value of gravity, or the acceleration due to gravity, is 9.81 meters per second squared. Now that's the average value. G changes all over the planet. It's different depending on a variable set of things. It depends on how thick the crust is at that point. It depends on what kind of materials are beneath the person. But it's not so variable where some parts of the planet G is 11, some parts are 5. No, it's all anywhere between 9.5 to 9.9. Gravity is about that all across the planet. You're not supposed to be using that value for any sort of calculations, right? But it is variable. I think gravity in the Caribbean is established as 9.65 or something like that. It's a little less because our crust is thinner at the Caribbean than in continental areas. So we do actually have a smaller gravity than other places, but not enough to make a difference anywhere. All right, so the average value of G across the planet is 9.81 meters per second squared. Please note G is an acceleration, so the units will always be in meters per second. Wonderful thing about being at CSEC level, they have decided, or they have allowed us to round up 9.81 to 10. So gravity is a very nice sweet number of 10 meters per second. So it's always easy to find, to multiply by G. All you have to do is just move a decimal point or multiply by 10. Please remember that gravity is an acceleration. The acceleration due to gravity is an acceleration, and you may have to use this value as acceleration in some questions. All right, moving on. An object falling will have an acceleration of G, no matter where we are above the ground. Now, we're not talking about going out in space 300 kilometers above this earth. No, we're not talking about that far away. We're talking about anywhere you would drop. So if I took the ground and I dropped a coin from 1 centimeter above the ground, the acceleration will be 10 meters per second squared. It doesn't matter where you are on the planet, right? If you are above, sorry, I just got an email from the school. Anytime you all see me look down at the corner there, I realize I got an email from the school. Say you are 10 kilometers above the earth and you drop something 10 kilometers from above the earth being the surface of the earth, your acceleration will still be g, which is 10 meters per second squares. It's a constant value, right? We assume that it's a constant value because the earth is so large. It pulls everything towards it at the same rate. So it's not to say a bigger object will have a greater acceleration than a smaller object. This is something that is falling, not something that we are pelting down. So if I just took something and released it and let it go, you saw it's not moving, just release it. It's going to fall at 10 meters per second square. So it's a number to remember. You're going to learn G is 10 by the end of the class. You'll remember that number, I hope. Actually, no, I lie. Some students reach form 6 and still trying to remember it. Falling with gravity. So we're going to learn how to work out questions using gravity or the acceleration due to gravity. By using the equations of motion, we can determine how high an object will reach when it is thrown upwards, how fast it will fall, and how long the time of flight was. Now, you all know this. If you were to throw something upwards, right? Do it right now if you want. Please don't throw something and land on your head. If it does, don't tell anybody because we will laugh at you. Right? If you were to throw something upwards, we all know it's going to reach the point, as in we throw it. We're not talking about taking a rocket and launching it with, you know, trillions of kilograms of force. Right? If you take something, launch it, throw it upwards, we know it's going to reach a certain height, and then it's going to fall back down. If you pay attention, go outside if you want, throw something like a ball or a basketball or something, throw it upwards, you're going to realize as it gets higher, it's going to appear to get a little slower. And then when it reaches its highest point, it will momentarily probably stop moving. It might stop too quickly for you to notice, but it will stop moving because at this point, the upward force that you throw the object with is now going to equal out with gravity, and then gravity is going to pull it back down. So you can throw something up, and there's going to come a point where you threw it up and it lost energy, and then it's going to start to fall down. So everything that you can throw up, right, without its own power supply and rocket launching behind it, anything that goes up will come back down. And the way how it operates, if you throw something up, it's going to reach a maximum height, right? And then when it reaches this maximum height, gravity is going to take over and it's going to fall back down. Now, if you start at a speed and it slows down, right? I throw something up that's going pretty fast. It's going to reach its maximum height, and by reaching its maximum height, it's going to come to a very short stop. That is called slowing down, right? And slowing down, that's if you remember from our last topic, indicates that it is decelerating, and deceleration is minus acceleration. So this leads us to the next note here. When falling, an object has an acceleration of g. That's falling, not being thrown downwards. You have to know the difference. Falling is when you hold it and release it. Throwing is when you take it and apply force for it to fall down. Two different things. When something is falling under the action of gravity, it does so with the acceleration due to gravity, and that is 10 meters per second squared. Now, when you throw something upwards, it's going to be acting against gravity. That's the same reason why going up a stairs is much harder than going down a stairs, because you're going against gravity. So there's an extra force pulling you down. So when something is being thrown upwards, it is going to slow down because gravity insists. Let's use the next color pen. Oh, good grief. Right? Gravity is going to be acting down. Gravity acts down all the time. So if your object is going to be going up, it's going to have this force that's in opposition to it, and it's going to want to slow down and then fall down completely. So here it's going to fall down, and by falling down, not being thrown down, this is where gravity acts on itself, because when it reaches to the top here, it stops moving for a very, very short time, and then it falls to the earth. It's not being thrown down to the earth. It's not being shot down to the earth. It falls to the earth. And because it's falling to the earth, gravity is the only thing that's pulling it down. So it falls with an acceleration of g, or 10 meters per second squared. So we want to look to see how we can calculate acceleration due to gravity questions. Now, there are some things you have to note. Let me just make these words a little bigger. Oh, this cannot be made any bigger. Let's zoom into you. Oh, that's too big. All right? When something is being thrown up, as in it's going upwards, you are going to be asked to find either the initial velocity, the distance traveled, or the time taken for it to travel. Why do we not know A and V? Because these two values are indicated by just saying something is being thrown up means that the acceleration is minus g. The instant you say something is traveling up, we know that the acceleration is negative g, right? And that is minus 10. And we know once we throw something up, it's eventually going to come to a stop at its highest point, and that means it's no longer going up. So its final velocity while traveling up will be 0. This is just the up section. If you look here in my diagram, we have a section for traveling up, and then we have a section for traveling down. So anytime something is thrown upwards, meaning you just take a ball or you take a pen or you take anything in your hand and you throw it upwards. All right. If you look at it, yeah, look, if you throw something up flat up like a book or your post-its, just throw it up. You'll actually see when it reaches its highest point, it momentarily just kind of floats in the air momentarily. I'll not say it's sitting down in air for like 5 minutes. Momentarily being a fraction of a second, it goes up, it appears to sort of hover for a little bit and then fall back down. All right, so what happens as it goes up, the acceleration is minus 10 or minus g. And in its action of going up, it's going to come to a stop. So that means its final velocity while moving up will be 0. So it's easy to calculate any of these values, considering you already know what v is, you already know what a is. Suppose I tell you something is thrown upwards with a velocity of 10 meters per second. It is easy for you to now go and calculate S and T, because you would have 1, 2, 3 values. We're going to go do a question and you'll see it just now. So that is going up. Now going down, when you have thrown your object up, oh, it's now falling down. We are talking about falling. Falling means it is stationary and then it starts to fall. When something is falling, the initial velocity will be 0, because falling means that the object was initially at rest. It is now falling with g, or falling with gravity, so the acceleration is 10 meters per second squared. I don't know where the squared went. And then they will ask you to find final velocity, how far it will travel, the time it will take to travel, because they might give you one of those. So just looking at your questions, when something is being thrown upwards, you already know 2 values. You already know that the acceleration is minus 10, the final velocity is 0. When something is being released, from above the ground, you already know two values. You know the initial velocity is 0, and you know the acceleration is 10. Just by saying whether it's going up or it's going down. Any questions yet before we try a question? Anybody?
Yes.
Okay.
Yes.
All right, so let's try a question. Now, you all don't have to wait on me. When you say a question, you all understand what to do. You could very well go ahead and start, doing the question on your own. So, example 1. An object is dropped from a height of 50 meters. How long will it take to reach the ground? Simple question, and realize, yeah, we can drop something. We can time how long it will take hit the ground, but we can actually work it out. So let's look and see. As we said, we are going to mine our question. We're going to see what values the question has given us. Where's my pencil? All right. So an object is dropped from a height. So we already know two things. If it's dropped, that means it is falling down. And once we're falling down, we already know what our U and what our A values are. We already know them. And it is dropped from a height of 50 meters. So that means it is now going to travel 50 meters before it hits the ground. So we know how far it's going to travel. And the question is asking us, how long will it take to reach the ground? How long it will take to reach the ground tells us they're asking about time. So let's put down our values. An object is dropped from a height. Drop means that the initial velocity is 0, the acceleration is g or 10, and it was dropped from a height of 50 meters. So that means that the distance traveled will be 50 meters. And they have asked us for the time. So what equation only has S, T, A, and U in it in your equations of motion?
The second one.
Second one, very good. So just working out here, we can see that we're going to use S is equal to UT plus a half AT squared. Now, those of you all who want to work it out, go ahead and all. All right, S is 50, U is 0, so this is going to cancel out. A half by 10 by T squared. So you're going to get 50 is equal to 5T squared. T squared is going to be 10. And this is going to give us, remember the reverse of square is square root. So T will be the square root of 10, which will be 3.17, 3.14, 3.16 seconds. So if I were on top of a very tall building that was 50 meters high, right? A 50-meter high building will probably be probably about 16 floors up. It'll be really high up. All right, so it will take 3.16 seconds to fall to the ground. So if you were on top of a tall 50-meter building and you started your stopwatch the instant you let go of that object, it would have taken a little over 3 seconds to hit the ground. All right, so that wasn't too hard by itself. So let's try another one. You all understood this?
Yes, yes.
Yeah, it was simple enough. Notice I didn't have to go through too much of the calculation because we've done this already.
Mm-hmm.
So this one you all are doing on your own. A pebble is thrown vertically upwards. So we already know two values with a velocity of 20 meters per second. So that means we are throwing it up with 20 meters per second, and it's going to go up and then stop moving as it goes up. Calculate the maximum height attained and the time taken to reach this height. So it is going upwards. So what do we know automatically just by saying something is being thrown upwards? Anybody?
V velocity.
The what?
V
See?
velocity.
The acceleration is -10.
Right. What about the velocity?
0.
What is zero?
That
Yet. Say it again.
um V is 0. That's
V is 0 because it's being thrown upwards. The final velocity will be 0. Now let's look at what other values they gave us. They said it was thrown with a velocity of 20 meters per second. So that means what is 20? I'm asking.
the, acc- the acceleration is
Final will be final. The final. Initial.
Initial. Remember, when something is being thrown upwards, let's go to that diagram again. When something is being thrown upwards, we know that the final velocity is 0 and the acceleration is -10. Right? Anytime something is being thrown upwards, we already know two values. Right? So we have 20, we have 0, we have -10 for the acceleration. And they have asked us, first things first, to find the maximum height. So that means they want us to find the distance traveled. So you have U, V, A, and S. Which equation is that? Let me just pull it down. Which equation we're using here, Olio?
Fourth.
info.
We're using 4, right? So we're going to use equation 4, which is V squared is equal to U squared plus 2AS, and I want you to find S. Go ahead, work that out. I'm going to give you like 3 minutes. Okay, let's do this very quickly. V squared is equal to U squared plus 2AS. V is equal to 0. Equal to U is 20, so 20 squared is 400 plus 2 by -10 by S. So that's going to give us 400 minus 20S is equal to 0. You carry this across the equal sign, you're going to end up getting 20S is equal to 400. S is equal to 400 divided by 20, and you end up with 20. End up with 20 meters. So it's the same questions we've been doing over and over. So what I do suggest, we do have, I think it's only one question I have in here, so you're going to give that a try. Not now, but oh wait, you have to work out the time taken to reach a site. So let's take 5 minutes to work out the time. So the next part, you're going to use time, considering, if I were you, use the easiest equation that has time, and that's always equation 1, because you know U, you know V, you know A, find T. So you all do that. You could do that actually mentally, you could do that. So if you wanted to work out T, all right, just really quickly, V is equal to U plus AT. V is equal to 0. U is 20 minus 10T, because A is minus 10. You carry this across the equal sign. You're going to get 10T is equal to 20. T will be just be equal to 20 divided by 10. You end up with 2 seconds. So it's not hard questions. And actually, in questions of throwing up and coming back down, you are given a little bit more information just by the question saying two things, either thrown upwards or launched upwards or falling down. Now at CSEC level, this is easy because all we are doing is looking at vertical, directly straight up and down motion. When you reach Cape, we're going to go from going up and down to start doing this. And that's a whole big other ball game. So let's see what we can finish up before the class finishes. Force. Let's just go through the type of forces and then we'll wrap up for the day. So force, the basic definition, As in really, really, really basic definition of a force is a push or a pull in really simple terms. But that doesn't really tell us what it is or how we can find out what it is. We can calculate force by finding the product of its mass and its acceleration. Acceleration, um, yeah, more mass and acceleration. Force is always measured in newtons, so we are meeting a brand new unit and a brand new quantity. So force is measured in newtons. The equation for force to calculate force is equal to ma, where a is your acceleration and m is your mass. So please note, if you had to work out the units for force, right? Force is mass by acceleration, because in multiple choice, you see things like these where they give you different forms of units to represent something. This usually comes from multiple choice. So how do I work out what are the basic units of force? We look at the equation and then we look at the units of each quantity in that equation. So the unit of kilogram, the unit of mass is kilograms. The unit of acceleration is meters per second squared. So what we're going to get? We're going to get kilograms meters per second squared. So if you want to write that down, the Newton is equal to a kilogram meter per second squared. So that's just the units. This kind of question will come in your multiple choice. So just be mindful of them. Types of forces. There are many types of forces since there are many ways by which an object can be accelerated. So we're going to look at some of the type of forces that exist. The most obvious one that we know of that keeps us on the planet, keeps us sitting, keeps us walking, keeps us within the nice confines of our atmosphere where we can breathe and we won't suffocate or explode or freeze, because if you go in space, there's a chance that you can explode. We're going to go through that later on. So gravitational force, these are attractive forces that exist between bodies due to their masses. Gravitational force of a planet on an object, well, we're going to go through this later, right? Next topic is an object's weight. Magnetic force, attractive or repulsive forces that exist between bodies due to their magnetic polarities. We're going to look at that. Electrostatic forces, attractive and repulsive forces that exist between bodies due to the electric charge. Electrons are kept in orbit around the atomic nucleus by such forces. You all doing chemistry, you all know that, because we have our negatively charged electrons rapidly spinning around our very positively charged core or nucleus. For nuclear forces, these are extremely powerful attractive forces which bind together the subatomic particles in an atom's nucleus, which are, quite frankly, the most powerful attractive forces in the universe. We have elastic forces. These are restoring forces produced when a body is stretched or compressed. So we're going to look at that in Hooke's law. Mechanical forces are those that exist between bodies in contact. These are pushes, pulls, normal reactions, and friction. So what we're going to look at, we just looked at gravitational force, so we're going to look at it just now again. In the topic of mechanics, we look at gravitational force, elastic force, and mechanical forces. So we're going to cover these three in this topic. Magnetic and electrostatics, we are doing electricity next term. So we look at that then. And nuclear forces, yeah, that is next term also. Going on mass and weight. Now, this is where physics differs from general life or real life because of not technicalities, because of detail and facts. All right. In regular usage, we often confuse mass with weight. Sorry about the sneeze. In physics, there are two very, very different things. Even though they're very closely related to each other, they are different. So let's see what the difference between mass and weight are. Mass is a measure of how much substance a body has, meaning your mass is just accumulation of all the cells, all the atoms that are in your body. This does not readily change, right? Or let's take an inanimate object. You're going to say, well, miss, we could lose weight or whatever. Yes, our weight fluctuates because we constantly, our mass fluctuates because we either are eating food, so we add in some mass, or we are losing some sort of mass by respiration or any other form of excretion, or even by breathing, we can lose a very small amount of mass. Very small. All right, but say I have, my little post-it here. My post-it, the mass of my post-it pad here is the sum of all the atoms in this post-it pad. No matter where I carry this post-it pad on the planet, and no, I'm not ripping it apart and some teeth and post-its from it. No, all right? Wherever I carry this post-it pad is going to remain the same post-it pad and the mass is going to remain the same. I can send this up on the next SpaceX flight to the International Space Station. This post-it is still going to have the same mass because the amount of molecules in this post-it did not change. And that is what mass is. It's simply telling us how much substance an object has. So continue reading. This value does not readily change and is measured in kilograms. So mass is measured in kilograms. We don't talk about pounds and ounces and no. We don't do those things. We're talking about SI units. Weight. Weight is the force exerted on an object as a result of gravity. So this is where you learn the actual definition of weight. Weight is the force exerted on an object as a result of gravity. So this means weight varies once gravity does. Weight is measured in newtons because it is a force. And how do we find the weight of an object? Weight of an object is its mass by its acceleration due to gravity or gravity. So your way to calculate weight, it is mg. So I just said that mass and weight are two different things, but look, I am looking at an equation where the two of them are in the same equation. So yes, they are related, but they are two different things. And let's see what the difference is. We have time to do that? Yes. Weight is always a force to consider in calculation. So please note, this is before you go on to the next part. Weight is a force. So sometimes when you get questions and they don't give you the force, you can always assume that the weight of the object is also the force of the object. But I'll remind you that later. So I want to compare mass to weight. We want to see what is the difference and we want to see what is the similarity, because as far as we know, when I ask somebody to go and find the mass of something, say you go in the market and you want to get, say, 2 kilograms of tomatoes, you're going to ask the vendor to weigh it. You're going to weigh something. When you go by the doctor, they weigh you. And when they tell you your weight, they usually tell you, well, you probably 60 kilograms or 150 pounds. Weight is not measured in pounds or kilograms. It is a force. So this is where in regular life we have gone to using weight, the word weight, not the term weight, the word weight to represent mass. But mass and weight are two very different things, and we have to learn to distinguish between them in our physics. So let's look here. This one drives home what is the difference between the two. So I'm going to look at the mass and weight of a large rock that has a mass on Earth of 1 kilogram. And I'm going to look at the Earth, Moon, Jupiter, and general space. Space being far away from it. So the mass of the rock. I can take that rock and carry it anywhere. I can take that rock, walk around the earth. It's still going to be 1 kilogram. That rock is not going to change. I can take that rock and put it on the next probe that is going up to the moon, and it's still going to be 1 kilogram of rock because your mass tells you how much substance is in your rock, all your molecules added up together. No matter where you go, that does not change. Um, then we could take that rock and hypothetically take it to Jupiter, and we could just see what it is in space. No matter where you are, the mass of that rock is 1 kilogram. The sum of its um, molecules is the same no matter where you go. But now let's look at how the weight changes. The gravity on Earth is about 10 meters per second squared, as we just did. The moon, gravity on the moon is about, actually, no, this is the wrong value. Whew, how did I do that? Right? Just now, that's the wrong value. 1.6. Gravity on the moon is 1.6, right, meters per second squared. The gravity on Jupiter is 24.8 meters per second squared. Yes, we have sent probes to Jupiter. We do know how great their gravity is, and actually, when you reach lower 6, you'll be able to calculate how great a gravity on a planet is just by looking at the size of the planet. That's how we know what the gravity of the sun is. No, we've never sent a probe into the sun. It will burn up before it even reaches. And gravity in general space is 0. So I want to find out what is the weight of my 1 kilogram object.
Miss, but you never say what's the gravity on Mars.
What's the gravity of what?
On Mars.
The question have mass?
Oh. Wait, so is the question? Oh.
You see
Oh.
what we're looking at, right?
Yeah, I know, but I asked any question. I asked
Okay.
him.
Right? Mars is 1/3 the size of Earth. Take off your mic, Malika, sorry. Wow, that was really loud. This is why I had mixed it up. The original question in this was Mars, and the gravity on Mars is 1/3 that of Earth, and it is 3.33 meters per second squared. Right? Those are the planets that, the objects that I know. The gravity on Venus is nearly identical to Earth because Venus is very, very, very closely, nearly the same size as Earth. Can't remember the rest, but that's easy to find. Just go and Google it. So I want to now go and find the weight of my object in these four locations. So weight is mass by gravity. So here it's going to be 1 by 10. You're going to get 10 newtons. So on Earth, a 1 kilogram object is going to have a weight of 10 newtons. On the moon, it's going to have a weight of 1.6 newtons because 1 by 1.6 is 1.6. That's why when you saw videos of the astronauts on the moon, they could have jumped so high because their weight was so small, right? They effectively became very, very light. Their mass did not change. They did not lose, all the air in their body. They didn't lose a leg. They didn't lose an arm and got lighter, meaning less mass. But what did change is that the gravity that is acting on them was much smaller. So they were able to jump further, right? Using the very strong muscles that they have that are built to handle Earth. On Jupiter, it will be 1 by 24.8. So the weight of the object will be 2.4 times heavier on Jupiter. And in space, 1 by 0 is 0. It will have no weight whatsoever. Now, this is where you can see the difference between weight and the difference between mass. The weight tells us how much force is acting on the object or being exerted by the object. Mass tells us how much is inside of that object, how much material, being how many atoms and everything put together, is inside of that object. So one remains constant and one can vary because the value of G changes from place to place. So this is why mass and weight are two different topics. All right, everybody get that? That made sense? All right, so from now on, we try to not mix up the two terms. I'm sure a couple of you all saw that I had crossed off weight in your plan design lab and replaced it with the word mass. I'm sure you understand why now. All right, because when we're looking at mass of an object, that is something that remains constant. Weight does not remain constant because g is always changing. Remember I told you, even on earth, at different places on earth, g is different owing to a whole bunch of other factors. It's not so large, but say when you have really fine calculations to do, it makes a difference. All right, so from now on, please try to make the effort. I will correct you and I will remind you. Mass tells us about kilograms, weight tells us about newtons. So when we're looking at something that remains constant or we're measuring something with a scale, we are going to talk about kilograms and mass. Everybody, is that clear? All right, we do not talk about weight when we are looking at the mass of an object. Weight is something different. We use weight to calculate force. Mass is an inherent property of an object that does not change unless we physically change that object. Meaning cut out a piece or hydrate it or dehydrate it or something. So we're going to wrap up there for today. I usually put a note here so I can remember where we've reached. Just to look at the next day, remember I said we can have a class tomorrow because we only had a class one day this week because of the timetable. What time do you all want to have class tomorrow? Between periods 1 and 3.
We only